The launch of an Ariane rocket involves tremendous forces. The engines produce high-frequency vibrations that shake the rocket's entire structure. The airflow induces aeroelastic forces that strain the material to the utmost. Every potential source of failure must be eliminated as early as possible. Therefore, numerical simulation is used right away in the early design phase of the spacecraft. The finite element method is state-of-the-art in simulation for automotive engineering as well. The car is modeled using small virtual components called finite elements. These elements comprise all physical features of the structure. Being able to study the detailed behavior, engineers learn about the interaction of components, and they discover where a construction may be improved. The prediction of possible failure modes is used to improve vehicle safety. Numerical simulation with the PERMAS finite element system helps save time and development costs in the automobile industry. PERMAS was developed by INTES, a software company based in Stuttgart, Germany. Managing Director Reinhard Helfrich wanted to offer a multi-purpose simulation software.
We started with mechanical applications, including static and dynamic analysis. And over the years, the system has been extended to other areas like acoustics, heat transfer, and electromagnetic fields. Recent topics of interest deal with coupling these different field problems. The simulation of coupled physical phenomena has been a major area of development at INTES. Optimization is becoming increasingly important, hence the finite element methods in PERMAS are augmented by appropriate optimization strategies.
Optimization of components, like this cover for a differential. Industry is forced to reduce production costs. At the same time, product quality must be improved. One particular strength of PERMAS is its module for contact analysis. This type of analysis is particularly important for heavy transports, especially where it is impossible to test prototypes. The offshore platform Oscar B is assembled right at its final position in the North Sea. Ships carry the components to their destination. Some of the modules weigh up to 15,000 tons. Special vessels are designed to carry them. In order to simulate the different loading conditions during transport, a contact analysis has to be performed that accounts for the weight of the ship as well as the force of the waves. The versatility of PERMAS also offers advantages in the area of commercial vehicles. Vibrations induced by rough streets and the engine cause extreme loads on the material. The auto part supplier Behr in Stuttgart uses their test rig to determine the life cycle of a radiator under realistic conditions. The results are compared with the virtual model and then used as input for the optimization process. The complex geometry of the cooling fins is simplified for the simulation model. Modal analysis is used to identify the natural vibrations for the simplified model. Early use of computer simulation helps reduce testing during development. The resulting reference points for the experiment are transferred to the real radiator. Accelerometers are placed and vibrations are induced in the radiator. Now the eigenfrequencies for the real component can be compared directly with those of the simulation model. This procedure quickly leads to an optimized design for the radiator. In the early 70s, most engineers were skeptical about the finite element method. The success of computer technology could not be foreseen. A large contract from the aerospace industry enabled engineers at the University of Stuttgart to push the development of computer-based simulation methods. They developed their own finite element system, which enabled them to study the deformation of an aircraft fuselage during landing. The same engineers utilized the finite element method in civil engineering. The first application was the roof of the stadium for the 1972 Olympics in Munich. The roof was designed to blend into the landscape and, at the same time, to guarantee television coverage of the Olympics without cast shadows. Only a support-free and translucent construction would meet these requirements. Therefore, a net construction made of steel cables and acrylic glass panels was chosen. Using their simulation software, the engineers from Stuttgart were able to find the ideal form of the roof. They also had to compute the position of the joints and the exact length of the cables. The methods usually employed at that time could not fulfill the demand for accuracy. Even a minimal error would have had a severe impact on the stability of the roof. The roof of the Munich Olympic Stadium is still the largest support-free roof worldwide. The computer model had a size of 10,000 unknowns. Today, models with 50 million unknowns can be computed. In 1984, engineers from the University of Stuttgart founded the INTES company. More than 30 employees developed the PERMAS system in close contact with their customers. Training is another important activity. The PERMAS system integrates state-of-the-art numerical simulation methods and utilizes computational resources in an extremely efficient way. The size of the models is not restricted by PERMAS, but only by current hardware limitations. Customers save time and costs in developing new products. PERMAS integrates new hardware architectures. A parallel computer with multiple processing units performs a simulation in only a fraction of the time needed on a single processor machine. In addition to software development, INTES carries out structural simulations on commission. The Users' Conference, organized by INTES, is a forum for mutual exchange of experiences with PERMAS. Lectures and discussions help to foster ideas and suggestions by the customers. PERMAS is a software system made by engineers to be used by engineers. The automotive supplier ZF in Friedrichshafen has been using PERMAS for many years. Andreas Steinert explains the advantages of the system.
One of the main advantages of finite element simulations is the fact that we can start with our studies long before the first prototypes are built. The components only have to exist as computer models. We can perform detailed analysis even at this early stage. Many different variants can be studied by modifying the computer models.
Before variants can be analyzed, a three-dimensional scheme of the component is needed. The engineer enters meshing parameters like size and type of the elements and the material properties. The meshing is done automatically by the computer. In the next step, the engineer defines boundary and loading conditions. In order to achieve a realistic loading, the adjacent drive shaft is modeled and subdivided into finite elements. After the parts are joined, computation may be started. PERMAS provides numerous interfaces to other programs. This simplifies the exchange of data with different CID systems, pre- and post-processors and other simulation programs. The animation of the results clearly shows the weak spot, which is dyed in red.
These fins here are already in place. And here we see the maximum deformation.
The results at ZF in Friedrichshafen, the engineers optimized the housing by various measures, including an improved arrangement of the fins. Today, finite element simulations are employed in all sectors of industry.
In the early days, the finite element method was a mere computational tool. It's fascinating how today it's used to gain fundamental knowledge about technical components. Thus, the software becomes an innovative driving force for industrial development.
This innovative power was first used in areas like aircraft design, where testing is particularly difficult and at the same time a high level of safety and reliability is required. Today the goal is to replace testing completely and to build the first prototype shortly before the start of production. The use of PERMAS helped minimize launch failures of the Ariane 4. 113 out of 116 launches were successful. INTES offers efficient and reliable solutions for all areas of simulation. You can count on us.